I'm a member of the high-performance computing group of the La Laguna University. I will talk about Paralldroid, a source-to-source framework for simplifying the use of efficient code in Android. The development of efficient code is a complex task. Language that allows an efficient use of computational resources usually are complex and require an expert programmer. In the scientific context, we had a set of tools that simplified the development of efficient code. OpenMP is a standard designed to simplify parallel programming to share memory system. In this case, the programmer designed or defined his code and insert a set of directives. The compiler uses the information of these directives and generate parallel code that can be used in a shared memory system. OpenACC follows the same idea, but in the context of accelerator, like GPUs. Now we are going to do a quick introduction about the Android programming model. As an example, we are going to use a simple program, a transform to imagine to a grayscale. The most used is the programming model most used is based in Java. Java is well known and easy to understand. The Java code is compiled using the Java compiler, and the bytecode obtained is compiled using a DEX compiler. As you can see, in this example, we have a loop, get its pixel, get the color, and transform to grayscale. Another programming model is the native C model. In this case, some section of the application can be implemented using a native C language. This model is often used to reuse existing code library written in native C language. This native code is compiled using the native compiler. The complexity of this model is high, and the implementation is divided in two sections. A Java section, where we load the native code, call the native function, and define this native function. The other section is in C code, and is the definition of the native function. As you can see, this code is more complex than the Java implementation. The next model we consider is Renderscript. This model is designed to accelerate some section of the code. When Renderscript code is compiled, two codes are generated. Bytecode for a low-level virtual machine, in this case, and Java code for access to elements of the defined in the Renderscript code. Renderscript simplified the implementation of efficient code, but the problem is that Renderscript is a new language and have a new parallel model. The programmer have to learn how it works. The implementation have two sections. The Java section, where we create the Renderscript context, allocate the memory, and call the Renderscript function. And the Renderscript implementation, the Renderscript code is similar to C, but with some extension, like vector operation. Another model is OpenCL, and OpenCL is designed to accelerate some section of the application. Its implementation is defined in the native model, and OpenCL increases the complexity of the native model. Java implementation is similar to that present for the native model. The only difference is the load of the OpenCL libraries. The implementation of the OpenCL code, the native code, is more complex when we add the OpenCL code. Ideally, programmers implement their application using a simple language, Java in this case, but they want efficient code like Renderscript or OpenCL. So we develop Paralldroid, a source-to-source translator that generates efficient code from annotating Java code. The set of annotation used is an extension of OpenMP4. It is under development, and its latest release include directives for accelerator, like GPUs. This is an example of a Java implementation of great scale problem, and that can be used the directive. The directives can be used. The Paralldroid process is in the top level here. Is responsible of analyzing the Java code, looking for a directive. The file that don't contain directives are compiled directly. If Paralldroid find a directive for OpenCL or native code generation, this code is generated, the native or OpenCL code, and the Java code is modified to access the generated native or OpenCL code. And the same process is used for Renderscript code. This is the set of directives supported by Paralldroid. Target data directive is responsible of mapping the data to the context of the accelerator. Len is an extension of OpenMP standard, and we use it to indicate the target language that we want generate. Renderscript, native, or OpenCL. The map clause indicate the data that must be mapped to the accelerator. We have a different type of map. A lot that only create the variable, two that create the create and initialize the variable, from that return the values of the variable, and to from that initialize and returns the values of the variable. The target directive is responsible of mapping the data and execute the code associated to the directive in the accelerator. These clauses have the same function. This clause has the same function as in the previous case. Parallel for directives should be used in the context of a target directive. This directive is applied to a for loop and is responsible of distributed the load of the for loop between the thread available on the accelerator. Private clause indicate that each thread has a private copy of the variable. First private is the same, but in this case, the variables are initialized. Char indicate that all thread share this variable. Collapse is used for nested loop. The load of all nested loop are distributed between available thread. RS vector is an OpenMP extension, and it is used for Renderscript code generation, and indicate the input and output vector used in the parallel function call of Renderscript. Team shall be used in the context of a target directive. This directive is responsible of create team or group of create a group of team or of thread. Num team indicate the number of team. Num thread indicate the number of thread of each team. Private clause indicate that each team have a private copy of the variable. First private is the same, but the variables are initialized, and char indicate that all teams share the variable. Distribute shall be used in the context of the team directive. This directive is similar to parallel for, but in this case, distribute the load of the for loop between all teams available on the accelerator. And the clause are similar to parallel for case. It is an example of how to use the directive. It is the Java implementation of the great scale program. Currently, the translator doesn't support work with objects. So we transform the bitmap object into an array of pixels. And the rest coded traverse the array of pixels, get the color, and transform to create scale. To generate a render script, we add the directive. Target length and render script for generate render script, and mapping the variable. And we add the parallel for directive and assign the private variable and the input and output vector for render script. In some case, mapping of variable can be automatic. For example, in this case, all variable can be. In this case, all variables are read only. So if we don't define this variable, will be assigned automatically to the two map, the map of type 2. So they can be omitted or removed. And the same for write only variable. This simplifies the definition of directive. To generate a native code, we add a target length native, and in this case, we don't want initialize or return the values of any of these variables. So we use the map alloc. For OpenCL, we add the target length OpenCL directive. We define the team. Num team is work group in OpenCL, and number of num thread is a word item in OpenCL. And next, we distribute the load of for loop between all teams. To prove the performance of Paralldroid, we use two devices, a Samsung Galaxy S3 and an Asus TRON4 Prime. This device has a quad-core processor, 1 GB of RAM, Android 4.1, and this device don't support OpenCL for GPU execution. We use a set of problems defined on the Renderscript benchmark. Grayscale, convolve with kernel of size 3 and 5, and level. And we implement a general version of the convolve. We use kernel of size 3, 5, 7, and 9. We have a version of each Android programming model for all problems. The ad hoc Java version, ad hoc native C version, ad hoc Renderscript version, and the version generated by Paralldroid. Generated native C version, generated Renderscript version, and generated OpenCL. OpenCL version cannot be executed in this device. All tests has been done using this image. This chart This chart shows the speedup relative to the ad hoc Java version. For the ad hoc Java version for Renderscript benchmark problem. The native version doesn't have the native version don't have difference between ad hoc and generate version in this case. Ad hoc Renderscript version get the best result. Due to this version is optimized and use vector operation. Currently, the translator doesn't obtain this level of optimization, but has a positive speed up. For the general convolved problem, for general convolved problem, similar results are obtained. As conclusion, the methodology used has been validated on scientific environment. We prove that this methodology can be also applied to non-scientific environment. The tool presented make easier the development of efficient Android application in Android. We get efficient code at a low development cost, and the ad hoc version get high performance, but their implementation are more complex. As future work, adding new directive and clauses to generate parallel native C code and parallel Java code, working with objects to generate vector operation and to be integrated into the activity life cycle of Sand. Thank you.